Hello everyone. Today we'll be talking about how to use Ansys Workbench Additive to simulate a couple of different metal additive manufacturing processes. Specifically, we'll be looking at directed energy deposition and additive friction stir deposition. Directed energy deposition, or DED, shown in the bottom left of your screen, uses a laser or electron beam to melt and deposit material that's either blown powder or wire fed. It's often used to build relatively large parts. The workflow in Ansys for DED is capable of reading machine G-code to create clusters of elements that are activated sequentially to follow the toolpath. This same workflow can be used for other additive processes, including Additive Friction Stir Deposition, or AFSD, shown in the bottom right of your screen. The AFSD process works by rotating and pressing solid feedstock into the substrate until friction causes the material to heat up enough to plastically flow. The material never fully melts, so this is considered a solid-state additive process. The main difference between simulating DED and AFSD in Ansys is that the material is activated at the melt temperature for DED, but a lower process temperature is used for AFSD. Both of these processes put a lot of heat into the part, causing thermal strain and distortion as it cools to room temperature. Simulating this process in Ansys allows us to predict and compensate for this distortion. It also allows us to get other results such as residual stresses, plasticity, and build plate distortion. Next, I'll show you an example of an AFSD model created in Ansys Mechanical. So setting up one of these DED or AFSD models in Ansys Mechanical is pretty straightforward. You go to the DED Process tab and open the wizard. The wizard is essentially a guided workflow where you'll set up things like the part selection, base plate selection, and then you'll click Next. You'll go through and you'll set up the material assignment, the process parameters, and all of those things. And then once you finish, everything will show up in the tree on the left here. The main thing that you'll be changing for setting up an AFSD simulation is that like I mentioned, the process temperature we use here will not be the melt temperature of the part, it'll be a lower temperature. You'll also need to go into the details of the part geometry and change the stress-free reference temperature to be the same as that process temperature. Another thing that the wizard will walk you through is loading in the G-code. So the G-code looks something like this. So this is the actual code that is fed into the machine, and each layer tells the machine where to move and whether to do that with the tool head on or off. And so we read this same code into Ansys, and we can use it to create these clusters. So I can show those here. I can also show the toolpath. So if I step through these clusters, so these are clusters of elements that are following the toolpath, which is the green line is the toolpath while it's depositing material, and the blue line is the toolpath while it's not depositing material. And you can see these are the layers of elements that we're going to be activating sequentially using element birth and death here in Ansys Mechanical in order to simulate this manufacturing process for DED or AFSD. So let me switch over to a version of the model that I've already solved. So these are the temperature results for the AFSD simulation. And you can see that we're activating these layers, these clusters of elements sequentially following the toolpath. When we do this simulation in Ansys, this is a one-way coupled transient thermal to static structural simulation, where the elements are activated at either their melt temperature for DED or process temperature for AFSD, and then allowed to transfer heat and cool down to room temperature after the build is finished. So once we've solved for this entire time temperature history of the manufacturing process, we transfer those results into the static structural analysis to calculate thermal strains, which cause our distortions and residual stresses. So here I'll show a similar animation of the total deformation. So again, activating those clusters of elements sequentially following the toolpath to calculate our distortion. In the structural analysis, we also simulate cutting the part off of the build plate. So the result you see here is after cooldown, just before we cut the part off the build plate. And then right here, we can show what the deformation is after cutting it off the build plate. And you can actually see that the deformation increased by about a factor of 4 when we remove the support of the attachment to that build plate. We can also look at other results such as equivalent stress as well as plastic strain. So this is how you can use Ansys Workbench Additive to simulate directed energy deposition and additive friction stir deposition. If you want more information on this or on other types of additive manufacturing processes that Ansys can simulate, please click the link in the description below.